Okay. But now okay, so even though we for our convenience we have put all those words, and now it's very easy to understand assembly language, but there's a problem. What's the problem? The processor will not understand this. Why? As processor understands only machine language, because it's embedded built in only machine language. You can give only machine language to the processor. So the processor won't, just because we like assembly language, processor won't know, because processor is always zeros and ones. It's a binary two-state devices. Okay, all the language embedded into that are also in binary. So only you have to send binary. No way you can use assembly language. So what do we do? So we use another software to translate the assembly language to machine language. Okay, and remember, this assembly language has to be translated to machine language. So let's see a diagram. Before we go to the diagram, there is a name for this. This translator, that is the translator who is translating the assembly, taking the assembly language and converting it to machine language, that translator is known as assembler. Okay, the translator who translates the assembly language to a machine language is known as assembler. Okay, and the assembler translate one instruction of assembly language to one of machine language. So let's see that example. Okay, so this is the assembly language instruction set we are having, and this is the assembler, that is the translator. This is also a software. Okay, it's a program, zeros and ones in this also, having instructions and whatever necessary to do the translation. Somebody has written this. Actually, the manufacturer of the processor only generally writes this, because they are the ones who know exactly what that particular processor understands. So they will write this assembler for assembly language to transfer. Why are they taking the time to do that? Because assembly language is much easier for human to read than the machine language. So people will prefer to write in assembly language rather than writing in machine language. So when you write in assembly language, the system won't work. So they write the assembler also, which is a translator. Now the computer is doing the another computer software is doing the translation. We don't have to worry about. So we can write in assembly language and let the assembler translate it. Okay, so example, look at this. We want to do the same one example. Okay, add 4 and 5 we want to do, right? So this is what we have written in assembly language. We have said add 4 and 5. So this add 4 and 5 will be taken by the assembler. Okay, 4 and 5, it will be taken by the assembler, and it will be, add will be converted to this, because this processor is machine language for add this we have seen in the previous slides, 4 zeros 1 1 0 0. So it translates to that. Then the decimal 4, it translates to binary 4. 5, it translates to binary 5. And this set, it writes into a secondary storage file. See, this one 100, this and this. So the machine language version is written into a file in secondary storage on your hard disk or somewhere. So once it is written, before that, this process of taking this, translating and writing is called assembly. Okay, this process of converting assembly language to machine language is known as assembling. So this process, the assembler is, what the assembler is doing is assembling. It's taking the add 4 5 assembly language version and converts it into binary version of, or a machine language version of that. So that process is called assembly. Okay, it writes into this secondary storage file, and as you know, whatever that is written onto your hard disk, whether the power is there or not, what you have in the hard disk will remain there. Next time also you can take. So then what happens is, after this is written, you can take your instruction from this and give it to the processor. The processor will do that. See, now the processor is not getting actually the add 4 and 5. What it's getting is the machine language version of that. And so when this comes in, add 4 and 5, it gives 9 out. This is binary 9. Okay. So let's see another example. This time we are going to compare both the processors. Assembly language instructions in processor A, assembler for processor A, and we are doing add 4 5. So again we have seen that it goes into the that 4 goes and then it translates add into this, 4 into that, same thing we saw in the previous slide, and then it writes that whole thing into the text file, and then in the secondary storage, and that's the secondary storage, and then from there the processor can take the instruction and do it. Now the advantage in writing this file is after it has written the file here in the secondary storage, you don't need this program anymore, you don't need this part anymore, because you can give this to the processor directly, run it. You want to do it again, you give it from here, again you give. You can give any number of times. Each of the time it need not do a assembling process or look at the assembly language, because it has the relevant machine language version of the commands already here in the file. So from here it can take and execute any number of times, 100 times, 200 times, 300 times, it just keeps on. So every time it's doing the running or executing this, it need not do any assembling process, or it need not need the help of any of these, because already the translation is done, it's written into a file. Now we can take it from the file and the processor can keep working. Okay, and look at this, the add is the add of this processor. Okay, this is binary 4 and binary 5, and that's the machine language version. This is, so these are examples. Okay, I'm just giving an example so you understand what this whole process is all about. Okay, and then you get the 9 out. Then if I run again this, again these things will go through the processor, again it will come out as 9, and I keep on doing that. Now let's assume I want to do a add 6 and 5, then only, that is when this has to be changed, then you have to change this, again assemble it and get the new version's machine language code. Okay, and then you can keep on executing that. So every time you need the originals, this is called the source. Okay, original source to have some change, what you already have is not correct, you want some different difference, you want to add 10 and 20, you want to find 100 and 150 or something like that, a different number. Then every time you want to do a change here, you have to do the change here, assemble it, and get the go through the assembling, and assembling process will produce this one with the correct relevant one for this, and then after that you can just keep using that to the processor to get the output from there. You don't have to do this. So only time you have to do is whenever this is changing. Okay, but here I am showing an example with only one instruction, but in actual situation it won't be just one instruction. You will have a set of instruction that you give to the assembly, it will take all and convert and put all of that here and keep it, and then you can keep running from there. So if anything is changing from that whole set, then you have to go and change those things, reassemble it, get this version. Once this version comes out, you can keep using that version and keep doing the program. Okay, so same example we'll see for computer processor B, using processor B. The first one is processor A, now processor B. So assembly language instruction we are going to write, and the assembler for B is there. Why U, B and A you have already seen, and I will show it again. Now again this computer also we are giving assembly language program to add 4 and 5. So again assembler will take 4, add then 4 and 5. Right, now this one translates the add, this assembler will translate the add to 110, because that is what the B processor will understand as add, whereas processor A will translate the add as 000110, because that is what is understood by this processor as add. So that is why it's machine dependent or processor dependent. Okay, so this one, this now, so I can't take this assembler and put it here, because this will be translated to this. If this assembler is translating, this program is translating this, it will translate to this. Yeah, that's what it's doing now. Okay, so vice versa, you can't twist. I can't take this and put there, I can't take this and take that and put here. Okay, the assembler for B has to be there when you are writing assembly language for B. Assembler for A has to be there when you are writing assembly language for A. Okay, right. Then the relevant B's assembly language, machine language version is done, and again similar to this, it will write onto the text file or a secondary storage file, and keep it. So from there you take that and you can give it to the processor and get the result 9 out. So in both cases you are getting 9 out. But the difference is this assembler converts the add to this assembler converts the add to this, and it could be all the other things also could be different, like just like the this example. Okay, so the machine language version of A is here, machine language version of B is here. So B will take from here and execute, A will take from here and execute. Okay, now if you try to give this to B, B will not understand that because this instruction set is meant for A. So that is why it's processor dependent. Okay, but see, the advantage is we are able to write the assembly language almost similar and in English like and decimal numbers rather than writing ones and zeros like this. Okay, that is the advantage of this assembler. Assembler will do the translation for us when we are allowed to write the instructions like this. Okay, the result is 9. So machine language and assembly language are both languages of the processor because that is the processor's language. No, only difference is machine language can be done by the processor without the need of a translator, because machine language is in ones and zeros. The processor can directly take that and execute as long as that ones and zeros is for that particular processor. Okay, but assembly language needs to be translated to machine language because assembly language is not in ones and zeros. So assembler has to translate that and convert to machine language before the processor can execute the machine language. Okay, and if you look at the two languages, machine language is user unfriendly because it's all zeros and ones and zeros and zeros and ones, very difficult for us to read. Whereas assembly language is much more friendlier than machine language. Okay, because this allows us to write things in English like words and decimal numbers, add and subtract and so on. Okay, right. So machine language and assembly language, both of these languages are known as low-level language. Why low-level language? Because they are the closest to the processor. Machine language directly works with the processor, same instruction set. Assembly language needs a translator, but still it's the same instruction set. These languages will not work with different processors. It will only work with the processor it is meant for. So that is why these two languages are low-level language, close to the processor, or in other words, the processor's language. Okay, they are the processor's language, and therefore we can call it these two languages, assembly language and machine language. They are machine or processor dependent. It will work on only on that processor it is written for. It will not work on other processor. Okay, so that brings us to the end of this lesson. Thank you very much. In the next lesson, we will see about high-level languages. Okay, thank you.